this evening, I want to discuss the researches in Kamioka. And here in this page, you see the map of underground Kamioka. And well, in this talk, I'm going to discuss the 30 years of research in the Kamioka area. And 30 years ago, we started with a single experiment. Now, we have this kind of experiments going on. Well, the outline of this talk is summarized here. I have a brief introduction on the location and also on neutrinos. And then I move on to the Kamioka experiment, which started more than 30 years ago. Then I move on to Super Kamioka experiment. And Super Kamioka discovered neutrino oscillations. In addition, the experiments in Kamioka contributed to the discovery of solar neutrino oscillations. And finally, before finishing, I want to talk about the future neutrino studies, and also I'm going to talk about the new research in Kamioka. That is the gravitational waves. Well, introduction. Well, first of all, you may not know where is Kamioka. Well, okay, Kamioka is there. And the site is something like that picture now. And of course, you don't see much human activity, then it will be extremely difficult to carry out experiments. Fortunately, there are some human activities there. Anyway, we do experiments in this kind of location. Now, well, you have already heard about the neutrinos, but let me repeat. Well, what are neutrinos? Neutrinos are elementary particles like electrons and quarks. Neutrinos have no electric charge. Neutrinos have, like the other particles, 3 types or 3 flavors, namely electron neutrino, muon neutrino, and tau neutrino. And neutrinos are produced in various places, such as the Earth's atmosphere. And they can easily penetrate even through the Earth. However, they can interact with matter very rarely. And therefore, we observe neutrinos when they have a very rare interaction. And finally, I want to say that in the very successful standard model of particle physics, neutrinos are assumed to have no mass. However, physicists have been thinking what will happen if neutrinos have mass. Then, more than 50 years ago, people realized that if neutrinos have masses, neutrinos change their flavor or type from one flavor to the other. For example, a muon neutrino could be generated at a point L equals 0. Then if they propagate, then they oscillate to other particles, for example, in this figure, tau neutrino. And if the neutrino mass is smaller, the oscillation length is longer. Therefore, by measuring the neutrino oscillation length, you can get the information of the neutrino mass. Anyway, in my talk, I'm going to talk about the discovery of neutrino oscillations. Now, I want to talk about the Kamioka experiment. The whole story started about 40 years ago. In the 70s, grand unified theories of elementary particles were proposed. Well, these theories were very attractive, and therefore we wanted to confirm these theories. And fortunately, very fortunately, they predicted that protons and neutrons should decay with the lifetime of about 10 to 30 years. Of course, 10 to 30 years is a long lifetime, but this is in fact measurable. Therefore, several proton decay experiments began in the early 80s, and one of them was the Kamioka experiment, or Kamioka nucleon decay experiment. In the left, you can see the sketch of the Kamioka detector. It is a 3-kiloton water detector. It has a steel tank of about 16 meters in diameter and 16 meters in height. And in there, we installed about 1,000 photomultiplier tubes to detect Cherenkov photons. And in the right, we show you the mechanism to detect charged particles in this detector. If a charged particle propagates in the water, then Cherenkov radiation is emitted. Then these Cherenkov radiations are detected by the photodetector, and using this information, we can reconstruct the information of the charged particle. That is the mechanism, well, principle of the Kamioka experiment. In any case, in 1983, we worked for the construction of the Kamioka detector. This photo shows how we worked for the construction of the detector. I said that the Kamioka tank was 16 meters high, but we needed to install photomultiplier tubes onto the wall. Well, 16 meters is a high, very high for us. Therefore, we discussed how to install the phototubes, and in the end, we decided to use rubber boats to install the phototubes onto the detector tank. Well, of course, working on the rubber boat is not a very pleasant working condition, but, well, of course, it's much better than falling off from the 60-meter high. So we did it. So we constructed the Kamioka detector and started the experiment in June 1983. As I said, Kamioka was a proton decay experiment, but we didn't observe any proton decay signals. However, it was found that the detector has a very good performance due to the 50-centimeter diameter photomultiplier tubes that were developed for the Kamioka experiment. Therefore, Professor Koshiba, who was the spokesperson of this experiment, noticed that Kamioka can detect solar neutrinos. Therefore, only several months after the start of the experiment, he proposed to improve the Kamioka detector to observe solar neutrinos. Also, he calculated the event rate of the solar neutrinos, and in fact, it was pretty low, maybe of the order of 1 event a week. So, at the same time, he proposed the idea of super Kamioka. which will be discussed later. Anyway, young collaborators, including me, had to work hard again in underground Kamioka in order to improve the detector so that it can detect solar neutrinos. These photos shows you our work during 1984 and 1985. The left one shows the construction of the side outer detector that was constructed between the steel tank and the rock wall. The right photo shows the construction of the bottom outer detector in the Kamioka tank. So we worked hard for the improvement of the detector, and well, we had several problems even after the completion of the modification of the detector. We had to improve the quality of the water, and it took us almost 1 year. And at the beginning of 1987, we were essentially ready for starting the solar neutrino experiment. And then, extremely fortunately, on February 23rd, 1987, we observed neutrinos from supernova explosion at Large Magellanic Cloud. We essentially observed only about 10, 11 neutrino events. But the consequence was so strong, this observation told us the mechanism of the supernova explosion. So with this measurement, Professor Koshiba received the Nobel Prize in Physics in 2002. Now, Kamioka had another measurement that was the atmospheric neutrinos. Well, Kamioka wanted to observe proton decays, but unfortunately, we didn't observe any proton decay. Instead, we observed a serious background to proton decay that are atmospheric neutrinos. So although the atmospheric neutrinos are unwanted, but anyway, we had to observe. And also we had to understand the atmospheric neutrinos. And during these studies, we found a significant deficit of atmospheric muon neutrino events. This graph shows the results from Kamioka and IMB experiments. IMB experiment was another proton decay experiment that was carried out in the United States. And both experiments observed a significant deficit of muon neutrinos. But, well, at that time, we had no idea what's going on with atmospheric neutrinos. We needed the next generation experiment to really understand what's going on. Also, in 1989, Kamioka succeeded in observing the solar neutrino signal. This is the first data from Kamioka, and well, we saw the excess due to solar neutrinos, but we also observed that the observed event rate was much lower than expected. Anyway, this is the observation of solar neutrinos and also the confirmation of the solar neutrino deficit. So, in the late 80s, Kamioka had, I believe, 3 significant results. That was the supernova neutrino observation, atmospheric neutrino deficit, and the solar neutrino deficit. And they were evaluated to be very important. Therefore, the construction of the Super Kamioka experiment was approved in 1991 by the Japanese government. Now, I want to move on Super Kamioka. Well, Super Kamioka is essentially a larger version of the Kamioka experiment. It is, again, a large water Cherenkov detector. It has about 40 meters in diameter and 40 meters in height. It contains 50 kilotons of water. And at present, we have about 140 to 50 collaborators from 8 countries. I said that in Kamioka, we had to install photomultiplier tubes. And that is also true in Super Kamioka. But in Super Kamioka, as you can imagine from this figure, there are much more phototubes compared with Kamioka. Therefore, we needed much larger number of people. And in fact, well, this photo shows the typical number of people worked in Super Kamioka for the construction of the detector. And I just want to tell you that maybe 80% of them are physicists and graduate course students, namely collaborators. So in Super Kamioka collaboration, we really worked hard to construct a detector. And essentially, we had to work for 1 year to construct the detector. Oh, by the way, in the middle, you can see a person who is Professor Totsuka and who was the first spokesperson of this Super Kamioka experiment. Anyway, after almost 1 year of work in Super Kamioka, we were essentially ready to start the experiment. This photo was taken in January 1996 when we started filling water into the Super Kamioka tank. You can also see in the right corner a boat, rubber boat, with 3 people on the boat. Unfortunately, well, we need a very clean condition in order to construct a detector or in order to operate a detector. So we try to make the clean condition. However, we were actually unable to control the mine air. So after 1 year of construction, mine air or dust falls onto the photomultiplier tubes. So we had to wipe off all this dust with these rubber boats. Anyway, we started the experiment on April 1st, 1996. And soon we started the physics analysis. And the first important result was the discovery of atomic neutrino oscillations. As I said, the previous experiments, Kamioka and Kamioka and IMB experiments, observed the deficit of atomic muon neutrinos. But we had no idea why the muon neutrinos show deficit. But honestly speaking, from the beginning, we thought maybe this deficit was due to neutrino oscillations. Therefore, we really wanted to get the data that can only be explained by neutrino oscillations. So we thought that maybe for neutrinos produced in our upper atmosphere, they just come to the detector. They only travel 10 or 20 kilometers. So they may have no time to oscillate. However, for neutrinos produced in the other side of the Earth, they have to travel long distances, typically 10,000 kilometers. So they may have time to oscillate. Therefore, we could see a significant up-down asymmetry in the data. And if we observe this effect, this could be a very strong evidence for neutrino oscillations. And in fact, this study was carried out in Kamioka, but Kamioka 3,000-ton water Cherenkov detector was too small. We really needed super Kamioka. Anyway, in 1998, we were ready to show our result. This transparency shows you our presentation in Neutrino 98 conference. And you can see two histograms. One is for electron neutrinos, the other is for muon neutrinos. And the horizontal axis shows the neutrino direction. One is cosine theta 1 means downgoing neutrinos, -1 means upward-going neutrinos. And you can see there is a significant deficit of muon neutrino events in the upward-going direction. That is the clear evidence for neutrino oscillations. In addition, at that time, super Kamioka had several other indications for oscillations. And the right figure shows the allowed region of neutrino oscillation parameters in 1998 by various independent samples. And all these analyses suggested that all the data are commonly suggesting neutrino oscillations. And from this, super Kamioka concluded that the observed Jeans angle dependent deficit and the other supporting data gave evidence for neutrino oscillations. Okay, that was for the atmospheric neutrino studies. In addition, experiments in Kamioka contributed to the discovery of solar neutrino oscillations. I want to mention a little bit about that. Well, maybe some of you may know, before this century, we had the solar neutrino problem. That was the observed solar neutrino flux by the pioneering Homestake experiment was much less than expected, about 1/3 of the theoretical prediction. That was the solar neutrino problem. And well, this problem was realized in the late 60s. Then the subsequent experiments in the 80s and 90s, including Kamioka experiment, confirmed the deficit of solar neutrinos. But no experiment was able to tell us the reason for the deficit. And the reason was finally known in 2001 or 2002 by the measurement of solar neutrinos in SNOW experiment. SNOW experiment is a 1 kiloton heavy water experiment. By using the heavy water, they can measure the total neutrino flux, that is the neutrino flux of nu e plus nu mu plus nu tau. In addition, they can measure the electron neutrino flux. Then the result is shown here. If they observe the total neutrino flux, the observed rate was essentially as predicted. However, if they observe electron neutrino flux, the observed flux was about 1/3 of the prediction. So that was the clear evidence for flavor change for solar neutrinos. Then what is the contribution of super Kamiokande? Well, the super Kamiokande data is shown in the middle. Super Kamiokande measures solar neutrinos by neutrino electron scattering. They are primarily sensitive to electron neutrinos, but neutrino electron scattering is also sensitive to mu neutrinos and tau neutrinos. Therefore, the measurement of the solar neutrinos by electron scattering gives the flux of the mixture of electron neutrinos and other neutrinos. And the discrepancy between the snow electron neutrino flux and the super K elastic scattering measurement gives us another indication for the finite nu mu plus nu tau flux. That is another indication for neutrino oscillations. By the way, with this measurement, Art McDonald received Nobel Prize in Physics in 2015. By the way, I want to mention another experiment. That is the Kamland experiment. Kamland is a 1 kiloton liquid scintillator detector and was constructed at the location of the old Kamiokande experiment after its completion. And it is a 1 kiloton liquid scintillator detector, and this detector is very sensitive to anti-electron neutrinos. Now, people realized that there are many nuclear power stations around Kamland at a distance of about 180 kilometers. So, Kamland could do neutrino oscillation experiment with reactor neutrinos. That was the motivation. And then Kamland had a very impressive result. This graph shows the survival probability as a function of L over E. And you can see the survival probability is minimized at L over E around 20, then gets to almost 1, then come back to low survival probability. That way, we realized that neutrino survival probability oscillate. And this is precisely what we expected by neutrino oscillations. And by this measurement, we were really confident that solar neutrino deficit was due to neutrino oscillations. Now, I talked about the atmospheric neutrino oscillations and solar neutrino oscillations. In addition, there were several other neutrino oscillation experiments. And by now, we understand the basic features of neutrino oscillations. That means neutrino masses and neutrino mixing angles. But, well, so far, I never talked why we think that neutrino masses are important. So, well, in the next slide, I want to convince you that small neutrino masses are important. Here, I plotted the masses of charged leptons and quarks. Now, we know neutrino masses through the information by neutrino oscillation experiments. Now, I try to plot the neutrino masses on this graph. Okay, the neutrino masses are here. So you notice that neutrino masses are in a far place. And in fact, if you count how far the neutrino masses are from those of the charged leptons and quarks, you realize that neutrino masses are approximately or more than 10 billion or 10 orders of magnitude smaller than the corresponding masses of quarks and charged leptons. This extremely small neutrino masses may not be able to explain within the framework of standard model. Therefore, we believe this small mass is the key to understand the nature of the smallest and the largest scales. That is the elementary particles and the universe. Okay, now, so far I discussed the neutrino oscillation experiments in the past. Now I move on to the future neutrino studies. Well, I said we had the basic understanding of neutrino masses and mixings. However, we think we still have many or several, at least several important measurements to be done in the future experiments. But today, since the time is limited, I only want to concentrate on one topic. Well, I showed you this graph. And in fact, I'm sorry, I didn't tell you. In plotting the neutrino masses this way, I had an assumption. If I remove this assumption, we know that there are other possibility. There is other possibility that is shown here. In fact, the vacuum neutrino oscillation experiment can only tell us the neutrino mass difference, absolute value. Therefore, in principle, the nu3 mass state, which is assumed to be the heaviest, might be the lightest. We do not know. Therefore, we need to test which is the true answer or true nature. Unfortunately, the current generation experiments are not powerful enough to answer this question. So we need the next generation neutrino experiments. And because of the importance of the neutrino masses, there are several future projects that are considered, planned, or in the construction stage. Well, this is the summary of the future experiments that can tell us the order or the neutrino mass order. So, because of the importance of the neutrino mass, there are many experiments planned. And in particular, I want to notice that we are really looking forward to seeing the result from the INO experiment. It's going to use atmospheric neutrinos, and it's going to use a very unique technique. So this experiment will be really very important for the neutrino community. Now, I want to move on to the completely different topic. That is the gravitational waves. This is a new research in Kamioka. Well, about 30 years ago, we had only one experiment That was the Kamioka experiment. Now, as I said at the beginning, this is the map of underground Kamioka in this year. Well, you can see that we had a huge development in these 30 years. Probably this development is due to the dynamics of the science, but anyway, we are now trying to do a new experiment that is the gravitational waves. And the gravitational wave project was evaluated to be very important fusion for the future neutrino, for the future Japanese cosmic ray community in the 1990s. But unfortunately, this project was only approved in 2010. So anyway, we are now in the construction stage of the gravitational wave interferometer in underground Kamioka. Well, of course, you have heard a lot about the gravitational wave from Professor Thorne. Therefore, I think I can skip this page. Also, I think essentially I can skip this page. Anyway, we are very much excited with the discovery of the gravitational waves in LIGO. Well, this discovery is really very important for us to keep our motivation. We really want to continue to observe gravitational waves. Now, well, you may ask, what is the difference of KAGRA compared with LIGO or European Virgo detectors? Well, we think we have at least we have two differences. One is in KAGRA, well, by the way, the name of the project we are doing now is the KAGRA project. One of the key features of the KAGRA is the underground location. Why underground? Because for us, the seismic noise is an issue. Therefore, we want to have the detector at the location where the seismic noise is small. And therefore, we decided to install the whole interferometer into the underground site. And typically, the seismic noise is reduced by 2 orders of magnitude compared with the surface. In addition, as we have heard this afternoon, the detection of the gravitational wave is a very difficult task. And finally, the thermal noise of the mirror could be an issue. Therefore, we decided to use cryogenic mirrors to reduce this thermal noise. So these are the 2 key features of the KAGRA project, and we'd like to get the high sensitivity with these key features. And I said that we started the project in 2010. Now we are in the middle of the construction stage. Of course, already all the tunnels were excavated, and we have the whole 3 kilometer by 3 kilometer vacuum tubes installed and leak tested. And we have many vacuum tanks for the mirrors. And in addition, we have the polished cryogenic sapphire mirror. Unfortunately, we have to use sapphire for the cryogenic mirror. And unfortunately, our mirror is not as heavy as those in LIGO. LIGO uses 40 kilogram, mirror, but our mirror is only 23 kilogram heavy. And KAGRA had its initial operation in March and April last year, and plans the first cryogenic interferometer operation in the spring of 2018 next year, and the high sensitivity run in 2019 or 20. But of course, you may ask, why you need KAGRA? Well, we think, well, of course, we are going to be a reasonably sensitive interferometer in 2020 timeframe, but we still think that KAGRA is important because, as already discussed, one of the main topics is the gravitational wave astronomy, and we have to work with the optical and, well, photon community, optical and infrared and so on. In order to collaborate with them, we have to tell them the location of the source of the gravitational waves. But, well, of course, oh, by the way, yes, of course, we think that LIGO India is very important. And, well, we think that LIGO India and KAGRA are very important because of the sky localization improvement. So with KAGRA and LIGO India, there will be a significant improvement of the sky localization, and that will be really important for the collaboration with the optical community. Okay, that's all. I want to summarize. Kamioka has been contributing a lot to basic science in the last 30 years and expected to contribute more in the future. Well, in the early 80s, Kamioka began to observe proton decays, but unfortunately, we didn't observe proton decays, but Kamioka observed supernova neutrinos, atmospheric neutrino deficit, and confirmed solar neutrino deficit. And this result gave strong motivation to construct Super Kamioka. Then Super Kamioka discovered atmospheric neutrino oscillations. The Kamran that was constructed after Kamioka contributed much to the understanding of solar neutrino oscillations. And now KAGRA is a new project trying to observe gravitational wave signals, and KAGRA would like to join the global gravitational wave network in a few years. And finally, I want to say that India is expected to play very important roles in basic science, such as the neutrino and the gravitational wave researches. That's all. Thank you very much.